right, we are moving on to 6.6, geometric sequences. So we've learned about arithmetic sequences. Arithmetic sequences was when you had an addition or a subtraction pattern. So a geometric sequence is going to be when you have a multiplication or division pattern. Okay, so it's an ordered list of numbers. Remember, the list does have to be in that order, otherwise you've changed what your sequence is. And it says the ratio between each pair of consecutive terms is the same. That's another way of saying it has a multiplication pattern. So when we were talking about arithmetic sequences, we use D for the common difference. That was your addition or subtraction pattern. We're going to be using R for this formula, and that stands for your common ratio, which is going to be your multiplication pattern. And notice I didn't say multiplication or division pattern. It's okay for you to find the division pattern, but when you're using the formula, you have to write it in terms of a multiplication pattern. So if you figure out that the pattern is dividing by 4, that's the same thing as multiplying by 1/4. So you would just make sure and write it as the multiplication format instead of as the division format. All right, so here is our formula. A sub n is equal to a sub 1 times r to the n minus 1 power. And the good news is the variables that we learned for arithmetic sequences still work for our geometric sequences. So a sub n is still the term that you're looking for. A sub 1 still stands for your first term. R is your common ratio, which is your multiplication pattern. And N represents the number of the sequence you're looking for. So if you're looking for the 100th term, you'd plug in 100 there. All right, so we don't always need that formula, just like with our arithmetic sequences. If it just asks you to find the next numbers, you're not going to have to use the formula. But if it asks you to find the 10th or the 100th term, that's when the formula is going to be more helpful. Okay, so let's take a look at our first problems. So it says to determine whether the sequence is arithmetic, geometric, or near. So arithmetic is going to be when it has addition or a subtraction pattern. Geometric is going to be when it has a multiplication or division pattern, and neither would be if it has neither of those. So on number 1, to go from 1 to -4 to 16 to -4, my multiplication pattern is by -4, which means it's going to be geometric. On number 2, to go from 3 to 7 to 11 to 15, my pattern is adding 4, which means it is arithmetic. And number 3, to go from 2 to 4 to 8 to 32. Well, if I look for an addition pattern, 2 plus 2 is 4, but 4 plus 2 is 8, so it doesn't have an addition pattern. If I look at multiplication, 2 times 2 is 4, 4 times 2 is 8, but 8 times 2 is not 32, so it doesn't work the whole way through. So that's why this one is neither. It almost looked like it could be multiplication, but then the 32 threw it off. It would have to be 16 for that next number. That one did have a pattern. The pattern was multiply the two terms together to get the next one. So 2 times 4 is 8, and then 4 times 8 is 32. So the next one you'd find by doing 8 times 32 to get the next one. But even though it has a pattern, it doesn't have the patterns we're talking about. All right. So it says to find the next 3 terms of the geometric sequence. So you need to figure out what the pattern is, and then once you've figured out the pattern, just extend it 3 more times. So to go from 7 to 21 to 63 to 189, I'm multiplying by 3. So if I multiply 189 by 3, I get 567. And if I multiply the next one by 3, I get 1701. If I multiply that by 3, I get 5103. So I just identified the pattern and continued it out. It's going to be more efficient than using that formula. Try the next 2. Okay, so on number 8, the pattern is you're dividing by 2, which is the same thing as multiplying by 1/2. So you just need to continue that. So if I do 72 divided by 2 or 72 multiplied by 1/2, I get 36. If I divide that by 2 or if I multiply by 1/2, I get 18. If I divide that by 2 or multiply by 1/2, then I get 9. And I can continue that pattern as many times as I need to. On number 9, I am multiplying by -2 each time. So 5 times -2 is -10, times -2 is 20, times -2 is -40. So my next number would be 80, and then -160, and then positive 320. So I can always just extend those patterns out to find the next numbers in my sequence. Okay, the next section says to write the next three terms of the geometric sequence and then to graph the sequence. So let's start by finding the next three numbers. So to go from 12 to 6 to 3, I'm dividing by 2 or multiplying by half each time. So my next one would be 3/4, and then it would be 3/8, and then it would be 3/16. And we talked about how to graph when we had our arithmetic sequences, and it's the same thing for geometric sequences. So for arithmetic sequences and for geometric sequences, we've talked about how it's an ordered list. So 12 is actually the first number in your list. 16 is the second number in your list. 3 is the third number in your list. 3/2 is the fourth number in your list. So you're going to actually have coordinate points. So this first coordinate point is going to be 1, 12, because it's the first term and 12 is the number. The second coordinate point is going to be 2, 6, because it's the second term and its number is 6. The next one's going to be 3, 3, and then I would have 4, 3/2 is the same thing as 1.5 if that's easier for you to graph it, and so forth. So we can take a look at what this graph would look like. Let's see, I'll go by 1s for my x-axis. I'm going to go by 2s on my y-axis. So 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, so my first one is at 112. My second one is at 2, 6. Then it's at 3, 3, which would be halfway here. And then 4, 1.5, and then it's going to keep getting closer and closer. We know it is exponential, so you can see it's coming down and getting closer and closer and closer to 0. It'll get closer and closer, but it will never actually cross. So it matches what we already know about our exponential equations, because geometric sequences are exponential because it has a multiplication pattern. However, oops, I made a mistake. Should I actually have connected those dots? It's a geometric sequence. It's only talking about those numbers. So really, I should not have connected those dots. Just the individual points are actually what we have. Okay? So we want to make sure we're being accurate with that. So if you drew the line like I did, go ahead and erase it and make sure you have just the individual points. So it's going to be the same thing for each of these next two. So try them if you want. I'm going to go ahead and go down to number 13 though, because we've already talked about how to practice graphing. And so it's the same thing. You just have to extend the pattern. You can graph as many of them as you need to. And then again, number 11 would be, you'd have the coordinate point 1, 3, and then you'd have 2, 12, and 3, 48, and so forth, because it's listed in order. Okay. Number 13 says to write an equation. So now we're using our equation. So our equation for our geometric sequences was a sub n is equal to a sub 1 times r to the n minus 1 power. Okay, so that's what we're going to be using. I like to put the parentheses around the r. You technically don't have to for the general formula, but it makes it easier when you're doing that substitution in. So I need to identify two things. I need to identify the first term, which is 6,561. And I need to identify the multiplication pattern. So to go, as I'm going across, I'm actually dividing by 3. Dividing by 3 is the same thing as multiplying by 1/3. So my r is going to be 1/3. All right, so if I'm writing just the general formula, that's a sub n is equal to my first term, which is 6,561, times my multiplication pattern to the n minus 1 power. So that's my general equation. Then it says it wants you to find the sixth term. So that means I'm looking for a sub 6. So I will plug in a 6 for each of my n's. And if I have 6 minus 1 for my exponent, I'm going to go ahead and just do that subtraction and make it a 5. I can write it as 6 minus 1 and then simplify it in the next step. I'm just going to go ahead and do that subtraction in the first step. And then I use my calculator from there. So you always do your exponents first, so I'll do 1/3 raised to the 5th power and then take that answer and multiply it by 6,561. And when I do that, I get my sixth term is the number 27. make sure you can actually plug that into your calculator. Don't just take my word for it. You have to be able to get that number. If you can't figure out how to plug it into your calculator to get 27, if you're getting a different number, make sure and ask me in class so that you can use your calculator. I always recommend practicing these problems with the calculator you're going to have access to on the test. So if you don't have your own calculator yet, you should be investing in one. Don't always just use the calculator on your Chromebook because you don't get to use that one, and you want to make sure you know how to use your calculator that you're going to have on the test. Okay, so number 14. So identify my first term. So my first term is 8. And then I identify my multiplication pattern. So my multiplication on this one, I'm actually multiplying by -3 each time. So then I can write my formula. So a sub n is equal to my first term. A sub 1 is 8. It didn't write very well. My first term times my pattern to the n minus 1 power. So now I'm looking for the sixth term. So a sub 6 is what I'm looking for now. So I have 8 times -3, and then it's 6 minus 1, which would make it the fifth power. So again, you're doing -3 in parentheses to the fifth power, and then take that answer times 8, and you get that the sixth term is going to be -1944. Okay. Try number 16. Let's skip down to 16. Okay, so this is the exact same thing, only they've given it to you in a table. You're still just looking at these numbers here. So you're finding the pattern there. My first term is going to be this one here. And then my multiplication pattern, well, on this one I'm dividing by 3, which is the same thing as multiplying by 1/3. So a sub n is equal to my first term times my multiplication pattern to the n minus 1 power. And I'm looking for the sixth term, so that means I'm looking for a sub 6. So 2,916 times 1/3. And then the exponent is 6 minus 1, which is 5. And it's not always going to be the sixth term we're looking for. It just happens to be that for this one. So I need to do my 1/3 to the fifth power first, and then take that answer times 2,916. And when I do that, I get the sixth term is 12. If you're looking at the 18, 19, and 20, these are the same thing, only now they've given it to you in graph form. You're still identifying your first term. So my first term is when x is 1, so that's my first term. To go from 2 to 6 to 18 to 54, I'm multiplying by 3, so my r is 3, which means that a sub n is equal to 2 times 3 to the n minus 1 power. If you're finding the sixth term, you're plugging in a 6, so you'd have a sub 6 is equal to 2 times 3 to the 6 minus 1 power, which is to the fifth power. And when I do that, I get that the sixth term is 486. Okay, so you can try 19 and 20, check and see how you're doing, and then go ahead and write your summary to make sure that you understand what we talked about, and then to see if there's anything you have questions on. If there's anything that didn't make sense, mark those and make sure in class that you're asking about those problems you're having trouble with.